The cam also. I let the cam.
Yeah, just let it.
Okay. So.
Yeah.
Go. So for the methodology, so here's the pipeline of how it works. We have the data, the LE clicks, scores, the grades, the dates of the assessment, and causal features are constructed using only data observable up to the current week. A risk model produces a weekly dropout probability. They show map that probability to support chair, and AI agent draft the intervention. The teachers review, edits, and send the message to the student. Each stage receives exactly what it needs and nothing it shouldn't yet know. The model predicts, the agent proposes, and the teacher decides. The dataset is OUTLAT, so the Open University Learning Analytics dataset, 32,000 real anonymized student enrollment across 7 modules. It records daily interactions with the learning platform, every assessment submission, and the final outcome of each enrollment. No synthetic data, the outcome label, fail or withdrawn, is that we predict. It never enters the future. So for the causal feature construction, this is the most important technical side. The leakage constraint is everything. A prediction made at week n can only use data observable at weekend. The cutoff day is simple, 7 times the week number. Any assessment due later, any click logged later is invisible to the model. This is enforced in the feature extraction code itself, not checked after the fact. The dominant feature, which I show after in the graph, is the on-time submission rate, the share of assessments already due that the student has already submit. About for the risk calculation, I use the EG boost, so the gradient boosted decision tree. I choose it over a neural network for interpretability and training stability on tabular data. The ensemble sums the outputs of many trees, each correcting the errors of the previous tree. The objective includes regularization to prevent overfitting, of course, and crucially, the trend test is grouped by student, so no student appears in the training and the test dataset. So the chair thresholds are explicit. So below 0.33 is chair 1, between 0.33 and 66 is chair 2, and more is chair 3. So for the result I had, because of the size of the dataset, I can only train it on 7,000 students. On the 7,000 we got, the student model has never seen, we reach an AUC of 0.92. That means in 9 cases out of 10, the model correctly identifies which of 2 students is going to fail or succeed. A precision of 0.89 means that when it flags a student, it's right like 89% of the time. Recall is on 0.79, meaning it's catch 79% of the students who do fail. We can note that recall trails precision. The system underflags rather than overflags. So for early intervention, the missed student is costlier error, so is a trade-off worth nothing. These three numbers summarize the key findings. A student who passed at their predicted risk fall from 0.87 to 0.12 by the end. So the model tracked the engagement improving, the AUC of 0.92 or on unseen student, and the separation between at-risk and safe student. As you can see from the week 5, you can already see that there is a gap between the two students. So we can already see early which student is going to fail or no. And for the data, so what we have, the most striking result is the feature importance on time. Submission rate is 0.47, nearly 5 times the next feature. The model is telling us something teacher already know, of course. It's not the grade that predicts if a student will pass or no, it's the silence. A student who submit work, even with low scores, is still engaged. A student who stops submitting is already leaving. By week 15, the trajectory is already predicted for all weeks. So clearly that intervention is not just possible, it's overdue if it didn't happen before. So the agentic layer as an engineering challenge, language model returns 3 text by default, so it cannot be stored or acted upon. We retry to emit a typed JSON, object matching a fixed schema, summary, risk factor, chair, action plan, and the mail we want to send to the student. 3 failure modes had to be handled. Reasoning model emit long internal monologues before answering. They wrap JSON files in Markdown fence despite instructions. And roughly 1-3 generation failed to parse on 7 million parameter model. The mitigation are stripping, structural recovery, and bounded retreat. 3 attempts bring the failure rate below 5%. So one further safeguard is that the model proposed is discarded and replaced by the chair computed from the actual restore. So we don't have any mistakes. And the model may describe severity. It may not decide it. So every interference on institution hardware, no student name, grade, or risk is transmitted to any external device. This is a design choice, not a constraint. Cloud APIs will work, but they will send data student outside the system. So for now, we can rewrite a model and we can see later how it will go with the API. And so what I want to be precise about this work, see what the work shows and what the work doesn't show. So what is it established is that the model separates future failure from past students and the student he has never seen. Separation between the risk student and not is visible by week 5, and the leakage is stripped by construction. But what is not established today, that this intervention change outcomes that claim that we need to try it on real students to check if the intervention of the agent is making them succeed in the grades. And predicting well and helping are different things, and only first is measured here. Outstanding questions include whether a teacher used the draft as written, whether the model transferred to this university data, and whether accuracy ought evenly across demographic subgroups. So to conclude, a model that predicts honestly, AUC around 1992, on unseen student, no leakage, resting on a signal any teacher will recognize, an agent that produces artifacts, not a chatbot, but a system that ranks, reasons and return a ready to send iteration plan from single button press that I will show you with the demo. So the teacher remains the decision maker. What the system removes is the excuse of not having time to realize that the student is struggling. So thank you. Now I will show you the demo.
So we here have also the demo or AI for education. So we can use video and demos and later we have questions.
Can you ask if they see the they see the video?
Yeah.
Okay.
Video. But we see the videos.
Oh, you don't see it here. Okay. The demo of our dashboard. So now we connect to the John Doe account. As you can see, the home of our dashboard. So we can move the weeks to see in the first lane, we can see the different tier, 1, 2, 3. At the beginning, low grade, so we have the big part of the student in the high risk. So I just click on the button, and now the agent is taking, and we will see what it will give us. So we have the chair distribution over the time, so we can see from the first to the last week how it goes with the different students. As we can see, the teacher can only see the student he has. We have the weekly schedule, so the courses he will plan for his students. It takes a little bit of time because it's running. Oh, I think it's okay. Yeah. So we have the cloud generated by the model. So it gives you the risk factor of the risk factors of the students, the action plan that he advised us to do, and he already written an email for the student, and the teacher can customize it as he wants to send it for to the student. You can see the action plan. Now we click on the student, we can see his trajectory. So the black one is the real, and the yellow one is what the model predict. And we also have